Okay, hello everyone. So this class we're going to continue with our discussion about the computational methods engineering. We're going to continue with the sample probability calculation. Okay, specifically, we're going to spend some time on the student t-test, and some other tests we can use to tell whether there are statistical difference between the sample and the population or between different samples. If we do a quick recap of last class we started about the sample probability distribution, right? So we started with first how to plot the probability distribution just based on the sample measurements. Because before, when we plot the probability distributions, we already have the functions for different probabilities or different distributions. For example, the binomial distribution, geometric distribution, Gaussian, which is normal distribution, log normal distribution. We have the equations, but a lot of times we only have the samples. We do not have these equations to plot the distribution. And here, this plotting position formula can help us plot or calculate the probability distribution or the exceedance probability just based on the samples we have collected. And further, we showed that when we collect samples from a population, and due to the limited numbers of the samples, there are always errors associated with our calculation of the mean, the variation, the variance, and also the skewness, right? So we said that actually the standard error can be further reduced by taking more samples, more number of samples from the system. And that's why these standard errors, which are shown on the right-hand side, are associated with the square root of n, right? Basically, the more samples we take, the smaller the standard errors for these calculated means, variance, or skewness will be. Okay, so we just started a little bit about this sample probability, right? So then a lot of times when we take the samples, we also want to test some hypothesis, right? To verify certain criteria. So if we go back to the example that we have been using, which is to evaluate the sample mean. So we were having this case that we are taking water samples, and especially some pollutants like the BOD, right? So we took 12 samples at the discharge point of a factory, right? The scenario is that we could be getting a mean of 35 milligram per liter, and then we find out the standard deviation is 6 milligram per liter. So we took 12 samples. We could be using these equations to calculate the mean and the standard deviation, right? And then, but the factory, it's basically creating or setting up this discharge point, saying that their water quality actually satisfy the EPA standard. And by the way, the EPA standard for BOD or BOD5 is exactly 30 milligram per liter, right? So the factory is claiming that they have a discharged water, or at least the water quality at the discharge point satisfy the EPA standard, which is right on the limit of the standard, 30 milligram per liter. While our sample measurement show a distribution, show a mean and standard deviation of 35 and 6 milligram per liter. And we showed earlier that for all of these measurements, actually they are associated with the standard errors. So then how do we see our data, right? So should we tell the factory that, well, 35, and this is the mean that we got, and it's clearly that 35 is larger than 30, and then we are going to issue a fine? Or if it's the other way, that we acknowledge that there are errors or standard errors associated with our measurement, right? And especially it has a pretty big standard deviation, right? You can think that 35 minus 6 is 29, which is below 30. So should we give this factory a chance or just to accept it, right? So, or in another way, can we set up certain confidence level that we can say that, well, 90% or 95% of the scenarios that the factory is violating the EPA standard, or let's say 95 or even 99% of the chance that they're okay, like the water quality that we sampled actually satisfy the EPA standard, right? So it's just acknowledging that there are just errors associated with our limited samples, okay? So if we put it in a more, let's say, a numerical way, right? So for example, we're giving real values of the samples that we're taking. So first we need to consider the population data. So population data is basically, you can think of it as the BOD concentration at any time of the discharge point, right? So it's going to have a very, very large sample. It's just that we're not measuring it, right? So we could assume, in this case, let's assume that the BOD concentration follows the Gaussian distribution or the normal distribution. And then let's assume that this is the concentration that we're going to see every second. Unfortunately, the BOD value or the BOD measurement has to be based on the bottles. So we cannot really, let's say, or we cannot really measure these samples or measure these concentrations at like a second-based resolution, right? So let's assume that these are just the second-based or 1 Hertz measurement of the BOD concentrations. So if what the factory was claiming was true, right? If it's a Gaussian distribution and then the concentration, the mean concentration, 30 milligram per liter, and this is the concentration that we're going to generally see, right? So for example, 30, let's say this is the current concentration, next second, 31, next second, 29, 30, 30, 28, 32, right? So you see that mean is still around 30, right? It's actually exactly 30 until now. And then 30, 27, sometimes it can be very low, relatively low, 24. Sometimes it can be relatively high, 40, right? 30, 30, 29, 28, 31, 33, so on and so forth, right? This is a population data, which is basically all the possibility of the BOD concentration at this discharge point. And as we said, we assume that it's a Gaussian distribution. So if you plot the histogram of all of these concentrations, you're going to see this bow shape or this bow curve of the concentrations. And now let's think about our sample data. Now we're using these bottles to take water sample and then analyze the BOD. So note that each bottle is only going to take 1 BOD value, right? So because of that, if we only take one BOD measurement, then there is a likelihood, right? There is certain probability that we could be taking this extremely high value, right? 40. Although it's quite rare, but you can actually calculate basically at this bottom, this Gaussian distribution, at least the probability is not 0, right? So because of that, if we just take one sample and then use this one single sample to judge the quality of the water discharged by the factory, it's not fair, right? Because 40 is, I would say, way over 30 milligram per liter. And we shouldn't be just taking one sample. And that's why we took multiple samples, right? We took 12 samples. So then let's say we're taking 3 samples, maybe taking 3 samples, then this is fine, right? We could be taking some values around 30, right? 30, 32, 33. The mean value is close to 32, right? So then, but it's still above 30, right? So should we accept it or should we issue a fine? Because theoretically, if this is indeed the water BOD concentration discharged by the factory, it is normal, right? It could be possible that we could be taking any samples. So, or samples with any values. So the lesson we learn from here is that to reduce the error of our sample, we should be taking more data, right? Instead of taking 3, we could take 12. But is there a limit, right? So should we take, let's say, 100 samples or 1,000 samples, right? Because we know that the more samples we take, the more efforts we're going to put, right? And we know that for the BOD measurement, it is not easy. It is quite labor intensive. And definitely we shouldn't be taking 1,000 samples, right? So then here comes the question. So how do we confidently say that the sample is indeed from the population, basically to show that, well, the water quality that we take from the sample represents what is being reflected in the population. So basically, if the factory is telling the truth, how can we confidently say that the sample we measured represents the population BOD concentration, right? So how can we confidently accept the result that, well, based on the sample data, although the mean value could be above 30 milligram per liter, but the factory is still following the EPA standard, right? Or if the sample reflects the mean value that's way above the population level, right? So how do we quantify this difference? So basically, how large can this mean value could be? right? How large can the sample mean value should be so that we can tell that hey, you're indeed violating the EPA standard, okay? So if you think about how to quantify this difference, right? So basically the question now is we should think of a parameter to describe the difference between the sample and the population with more confidence, right? So for example, if the sample water quality is indeed, let's say, different from what the factory is claiming, right? So we would definitely be seeing a mean value that's way above 30, right? So the first step is actually to consider sample average and the population average. So in this case, sample average, let's say we just use the X, right? X bar, let's put X bar, right? And then we use that to minus the population balance, which is mu. That's defined by the population, or that's defined by this factory. So for example, if we're thinking about the sample that we took here, then this t value or this difference, right, this parameter, right, would be 35 minus 30, which is 5. Okay, so basically this is the first parameter we can think of, and actually call this parameter as t. We can either use capitalized T or lowercase t. It is fine either way. But then this is the first thing we can think about, right? It's the sample and the difference in the sample average. And we can imagine if this t value is, let's say, 100, and we're taking 12 samples, right? There are 100 samples, and then it turns out that the mu that's claimed by the factory is 30, and then we're seeing an average of 130, right, milligram per liter of BOD. Then we can say, well, with more confidence, right, that the factory is violating the EPA standard, basically to show that the sample is different from the proposed population. And then the next thing is that, well, we were seeing this large difference, but we should also acknowledge that there is a sample uncertainty, right? There's always errors associated with these limited number of samples. And similar to here, right? So if we're seeing a mean of 32, around 32, then we shouldn't be really trusting this difference to be exactly 2, right? So then because of that, we also need to consider the sample standard deviation, right? It could be that we took samples of, let's say, for example, it could be we're taking the sample 20 and then the other one 40, right? And the other one being 32. And you're still going to get a mean value of around 32. But now you have a very large standard deviation. And if this standard deviation is true, then if you take another sample of 30, 35, and 40, then basically we can't rule out the possibility that this water sample still satisfies the Gaussian distribution and the EPA standard, because we know that there is a large standard deviation associated with the system, right? Or at least associated with the sample. So because of that, we sort of have to consider the standard deviation, then try to modify this T number. So we know that if we're seeing a large T number, but at the same time, the sample is showing a large standard deviation, then we have less confidence to say that the sample is different from the population, right? So because of that, we should be using the X bar. And then let's divide by the standard deviation, right? So basically, this is telling us that if the sample is showing a large standard deviation, although you could be seeing a large mean difference, right? The difference in the mean, we still cannot say confidently that the sample is different from the population, right? But on the other hand, if you see a very small standard deviation, for example, if you're measuring the BOD concentration to be 40, 40, 40, let's say 10 samples, all 40, we know the standard deviation is 0, right? So then we can say very confidently that the T is going to have a very large T value, very large parameter. And we can say very confidently that the sample is different from the proposed population, right? And then the next thing is that, well, we consider the standard deviation, but we also need to consider the number of samples we took, right? Because if we're taking 3 samples and if we're taking 5 samples, although they could be having standard deviation, similar standard deviation, their sample size is also going to lead to certain, let's say, the certain standard errors, right? So because of that, we use the concept of the standard errors here. And then what we do is we still use this t-value, and then we multiply by the square root of n. Let's say n to the power of 0.5. Okay, so note that this n here is basically outside this bracket, or if you want to show it in another way, you can do it as x bar we divided standard deviation divide by the sample number to the power of 0.5, right? The square root of n. Okay, so I would say this is a more appropriate t value, right? The expression of the t that you can imagine if we have a very large t value, right? So basically, it either means that we have a very large detected a very large difference in the mean, right? Or we detected a very small standard deviation, or we took a lot of samples, right? So if we have a very large t-value from our sample, from our sample calculation, then we can say that, well, the sample that we took is statistically different from the proposed population, right? So if you use the water quality as an example, the BOD concentration. So if we're seeing, let's say the sample measurement, we took, let's say 20 samples and then turn out to be 35, 34, 36, 35, 35, 35, so on and so forth, right? Most of them are being 35. We know that the standard deviation is going to be very small. At the same time, the mean value close to 35 and the difference is 5, right? So we're seeing a 5 divided by, let's say, standard deviation 0.001. And then we took, let's say, 30 samples. If we take 30 samples, then square root of 30 is larger than 5. So basically, we're going to see a very large t-value. A large t-value shows us more confidence, right? It means more confidence to tell that the sample is different from the proposed population. And we can say that, hey, this factory is violating the EPA standard. Okay. So basically, this is the t-value, right? This is the expression for the t-value. It's calculated by the sample mean minus the population mean, or the proposed population mean, divided by the standard deviation of the sample, and then in the denominator, further divide by the square root of the sample size, right? So if you think about this is division in the denominator, so basically the square root of n, if you show it outside this fraction here, it will be multiplied by the square root of n. Okay, so this is a t-value. And then basically, then the question is, well, how the t will distribute if the sample is indeed from the population? So we're asking the question in a different way. So here we're thinking of this parameter to show that the sample is indeed different. So now let's reverse, or let's change this question to be, well, how would the t-value look like if the sample indeed agrees with the population? Let's say how would the t-value look like for our water sampling problem if, let's say, the factory is telling the truth, okay? So now you would imagine, or you would expect a lot of values to be close to 30, right? There will be some uncertainty, right? So you would expect that the t will be taking the value of 0, right? Most of the time, it's going to stay at 0, because if indeed the factory is telling the truth, or indeed the sample belongs to the population, the mean of the sample is going to be very close to the mean of the population. And the standard deviation, or no matter how many samples you take, right, this t-value is going to get close to 0 if it's indeed from the population, right? So then this involves basically the process of the t-test, right? So basically, in the t-test, the hypothesis that we're making, or people also call it the null hypothesis, null hypothesis, or the hypothesis is that indeed the sample is from the population. So basically, the sample is indeed from the population, or if we use the water sample as the example, it will be this water sample quality is indeed as the factory claimed. So under the null hypothesis, so you would expect the t-value to be mostly around 0, right? So no matter how many samples you take, or if you take it today, tomorrow, let's say we take 1,000 samples of from the system, right? Do 1,000 examples and do 1,000 experiments, and each experiment we take 20 samples, right? So you would expect that the t most of the time will distribute around 0. So basically, null hypothesis has a more rigorous definition. So basically, it is a statement, statistical statement, that there's no significant relationship or difference between variables or groups. Basically, the sample is indeed from the population, often representing a default or no effect scenario. So that's called the non-hypothesis, the null hypothesis, right? So then the question, we're rephrasing our question here, right? So how will the t distribute if the sample is indeed from the population? So basically, if the null hypothesis is accepted, how will the probability distribution of the t look like? So now we're thinking about how will the t distribute, right? So we said that if we basically draw the distribution of the t, let's say this is our axis, this is another axis. So we know that the t could be taking positive or negative values, right? So because it really depends on how the Gaussian distribution of the water look like. Sometimes you could be taking a little bit higher than the mean, let's say water sample, right? So you could be having a mean value of 31, 30.5, but sometimes you could be having a mean value of, let's say 29 or 29.5. So the t can be positive or can be negative, right? So let me draw the t here. Then we can also put the function, the probability distribution function, right? So you can imagine most of the time it's t is going to be around 0. Right? If the null hypothesis is accepted, it will be around 0. But then the thing is that there will be probability that the t can be very large or relatively large. But if you consider the probability for those scenarios, it would be very low, right? Let's say go to infinity. There is that probability, but that's going to be close to 0. And then the same thing on the left-hand side. So basically, this probability distribution function is going to have a relatively large value near the center and then relatively low value near the edge, okay? And we know that it's not going to be linear for sure, right? Because it's going to show some curvatures there. And if you think about distributions like this, right, we talked about before, it will look like sort of like a Gaussian distribution, right? A bell-shaped distribution, okay? So indeed, the probability distribution function of the t look like Gaussian distributions, okay? So and then the t distribution, we call this as a t distribution. So the t distribution also depends on how many samples we have taken. So it depends on this parameter called degrees of freedom. So the degree of freedom is simply calculated by, let's say, if you're just comparing this sample from the population, basically the water sample from the let's say the proposed population, right? So it's one sample comparing to the entire population. Then the degree of freedom is just the number of the samples we take minus 1. So basically here, df equals 1, it means that we took 2 samples. df equals 3 means that we took 4 samples. df equals 21, we took 21 samples. And you can see that as we increase the number of the samples, it's going to show a even narrower, a more narrow bell shape, right? And this also makes sense because let's say if you're taking fewer number of samples, only take 2 samples, then there is going to be a higher probability that the t value is going to be taking the extreme values, extremely big or extremely small values, right? Because we know that there are standard errors associated with the limited number of samples. And as we take more samples, it's going to have this more narrow bell shape. And it turns out that when the degree of freedom is more than 30, people actually normally use the Gaussian distribution to represent the t distribution. Okay, so only when the degree of freedom is lower, then we're going to use the equation of the t distribution to determine to consider the probability of the t taking extremely large or extremely small values. And then let's get back to the question we had in the beginnings, right? So we're trying to find a parameter that can give us confidence to say that either this sample belong to the proposed population or either it's different from the proposed population, right? So then how do we quantify confidence, right? So confidence, if you turn it in the statistical way, basically it's probability, right? So we can say, let's say 95% of the probability that the T is indeed following the population, or 95% confidence that the T value is too big, that it's different from the population. And then if you show that in this way, in the probability distribution way, basically we have to find out the area. Basically, if we're saying that indeed the sample is from the population, then we would be integrating the area under this curve. So let's say we'll find the area or the critical T value, both on the smaller side and the larger side, that the area under this curve represent 95%, right? Because we know that the entire integral is 100%. So we will be finding out the area below the curve representing 95%. And if the T value is smaller than this critical T value, or if the T value is larger than this critical T value, then we say that the sample is different from the population, right? As simple as that. So basically, this is how we can use the T distribution to tell whether the sample belongs to the population or is outside the population. So we further consider the scenario of the one-tail test or two-tails test. So for our water sampling sample quality, or water quality example, we're going to use a one-tail test, because if you consider the T value, right, the sample mean minus the population mean, we actually only care about the scenario where the sample mean is larger than the population mean, right? So if the factor is claiming 30 microgram per liter, right? If we're measuring the sample mean of, let's say, 10 or 5, we don't actually really care, because it will satisfy the EPA standard. We only care about the scenario when the T value is too big, right? So if you reflect that in the T distribution, basically we want to make sure that we can find the critical T value, that if the T we calculated from the sample is smaller than this critical T value, and this critical T value represents 95% below this curve from the minus infinity to this point, right? So basically the probability above this T value represent 5%. If the T value that we calculated is smaller than this critical T, then we say that the water quality of the sample represent the proposed population. Basically, the factor is satisfied the standard, right? So this is a confidence level. We could be using different confidence level. We could be using 90% confidence level. So basically, it means that the area under this curve, still talking about the water sampling problem, so the area under this curve represent 10%, right? So 0.1. So basically, if you find out the critical T and then compare these critical T, if the T from the sample is smaller than the critical T, then we say that it's satisfied the EPA standard at 90% confidence level. It could also be 99% confidence level. So you can see, basically, if it's 99% confidence level, so we're going to see a very large or much larger critical T value. And what that means is that basically you have to see a very large T from your sample to say for sure that it is indeed above the EPA standard, right? Above the EPA standard. So there's 99% confidence level that we can say that it's the water sample quality is worse than the EPA standard. So there could also be two-tails test. So what the two-tails test means is that sometimes we want to make sure that our concentration is within certain range. For example, when we talk about one-tail test, we just need to make sure that the BOD level is below certain level, right? But then for pharmaceutical applications, we want to make sure that certain concentration is within a range, because we don't want the drug concentration to be too high, or we don't want the drug concentration to be too low. Otherwise, the medicine will not have any function. Again, it's going to involve this confidence level. We can say for 90% confidence level, but now this time we need to make sure that basically the critical T value that we're looking for, both below the area of the curve below this critical T and the area below or above this positive critical T, right? The critical T value, the areas added up together representing 10%, 0.1, because now we need to make sure that each of the probability represents 0.05. Right? And we also use this alpha to represent the basically the area or the proportion below this curve or above this curve, right? So the things are different for the one-tailed test or two-tails test. Another example, let's say if we're trying to make sure that there's 95% confidence level that the drug concentration is within the targeted range, then we need to make sure that the area below the critical T and the negative critical T and the area above the positive critical T each should be smaller than 0.025, okay? Because if you add these two areas together, they represent 5%, and that means that the rest of the concentration or the T values will represent 95%. So similar thing, if it's 99% confidence level, right? So basically we need to further push to the left or right, and the area represent 0.005, okay? So then we talked about this critical T. So how do we find the critical T? So we could be using this t-test table here, right? So if you don't have a calculator, or if you don't have a, let's say, if you don't have a computer, or if you don't have MATLAB, then we could use this table to find out the basically the critical T value representing different significance levels. So for example, we were talking about the either two-tailed test or one-tailed test, but either way, if you're looking for the alpha being 0.05, right? So then we can look for the alpha here, and then also depends on the degree of freedom, basically the number of sample we took -1, right? We could be taking 61 samples, right? So then the critical T value we should be looking at is 1.671. And then we can compare our measured T value against the critical T value to see whether the sample satisfy the proposed population. Okay, so this is what's called the student's t-test. So basically the theory under the student t-test is that if n random samples are taken from a normally distributed population with mean, this is proposed mean of mu x, and the sample mean and variance are x bar and xx squared, standard deviation will be xx respectively. The quantity t defined by this equation has a student's t distribution with n-1 degrees of freedom. Right, so we were talking about T distribution. This is the T distribution. So then you may wonder, why is that called a student's t-test? Okay, so at first, when I hear about the student's t-test, I thought that it's a bunch of students who find out this probability or this statistical method, and then we're honoring the student who developed this method. But actually, it is not the case. So it was first created by this English statistician W.S. Gossett. So he was working on this system and submitted this article, this research article, to a journal, but he wanted to use an alias, right? It's a pseudonym of the student. So you can see that it's the title, and then the author is by student. So it turns out that this method is very successful and became established. And instead of calling this method as the Gossett t-test, people actually use the student t-test, and it was widely used in the industrial circles and now in the academic or in research as well. Okay, so now let's do a practice of this student t-test. So we talked a lot about what it means, right? It turns out it looks like we need to calculate a t value based on the sample. And we also need to find out the critical t value, right, from the distribution or from the population. And then we just need to compare to make sure whether the sample is from the population or not. So this is the example. So analysis of 31 log concentration measurements. We're talking about log normal distribution. So if we're taking the log, then they satisfy the normal distribution, right? So they show a sample mean of 0.864, and a sample standard deviation of 0.42. It is proposed that the population mean is equal to 0.9. Right? So would you accept this hypothesis at 5% significance level? So here, this is more like a drug test, right? So for pharmaceutical application. So basically we took 31 samples, and it turns out that the mean is 0.8464, standard deviation 0.429. And then our target, right? So we're telling the customer that the concentration of this drug is 0.9. And then should we accept this result? Right, at 5% significance level means that a 95% confidence level. Okay, so based on the mean, you can see that it's lower than our target, but we have limited number of samples. We have this certain standard deviation. So can we say that this doesn't satisfy the standard or satisfy the standard? We have to use the student's t-test. Right, so we need to first find out how to calculate t. Right, so C clear. And then we need to calculate t, where t is going to be equal to the sample mean minus the proposed population mean. Right? And then we divide that by standard deviation, 0.429. And then we multiply that by the square root of the number of samples, which is 31 to the power of 0.5. So this is our t. And then the next, we need to find out at 5% significance level, right? So 95 confidence level, and we're going to do a two-tailed test, right? Two-tailed test, alpha is going to be 0.025. And then we said that there were 31 samples, right? 31 samples, so the degree of freedom is going to be 30. 0.025, it turns out that the critical t-value is 2.042. And one thing I need to point out is that this t-value that's shown here has a positive value, but basically it's also applied at the negative side. So for two-tails test, so the t-value that we should be looking at will be negative 2.042 to positive 2.042. So if the sample t is within this range, then we can say that at 95% confidence level, right, the drug satisfy the standard, satisfy the requirement. If the t-value is outside negative or is below negative 2.042, or if the t-value of the sample is above positive 2.042, then we say that it doesn't satisfy the population or the proposed population, right? The null hypothesis is going to be rejected. So then basically TC, we said is 2.042, right? And then we can do the calculation. Turns out that T is minus 0.4672 and within the range of -2 and +2, right? So it means that basically it satisfies the standard, right? So this is the t value we calculated, right? So since it's for this case falls within the required range, the hypothesis that the population mean is equal to 0.9 log of milligram per liter is accepted at 5% significance level. In other way, 95% confidence level. Okay, so this is basically how we can calculate using MATLAB, and in Excel we could not Excel in I mean, this is how we can calculate by pen and pencil, right? So we list out the equation and then get the result. So in MATLAB, there is this t-test function which can allow us to do the student t-test. But the only thing is that for the t-test function, you have to provide the real sample data. So what it means is that, for example, this is a MATLAB t-test. Right, so this is a t-test function or t-test2 function. So this is one sample and paired and two sample paired. So basically it's doing this one tail or two tail test, right? So so the problem is that if you want to use the t-test, you have to provide the array of data, the real sample data. But here, if you see this problem, basically it's just telling us the mean and standard deviation, right? It doesn't give us the 31 samples exactly. So because of that, we can't really use the t-test function, but here I can briefly show you how we can use this t-test function. So here, for example, if we're using the water sample as a water sample, like the BOD measurement as an example again, so we could be having BOD of, let's say, 32, 35, 40, 33, right? 32, 31, 38, 29, sometimes 28, right? And then 40 or 50, right? So basically we're leaning the BOD to a larger value. And now you can see that mean could still be around 30 or 40, between 30 and 40, but most of the data are above 30, right? So just based on our gut feeling, it looks like it's going to be outside the range, right? So, but we have to find out what is the confidence level. Okay, so then this is our BOD. We took how many samples? Or we took 10 samples, right? So then we can do the t-test or this H. We can do this H and P. And then t-test BOD. And then we can provide the mean, which is X and M. M will be the proposed mean. Let's see, click on the M, right? The hypothesized population mean. So then we can put the mean, let's say, put the EPA standard, right? This is what the factory is proposing, right? Then it's going to give you H being 1, basically means that the hypothesis is rejected, okay? The hypothesis is rejected. Let's see. Right, if H is 1, that rejects null hypothesis. Basically, it's telling that the sample is different at 5% confidence level, or 5% significance level, which is 95% confidence level. Okay, so we can also change it to another way. Let's say we're having some values of, let's say, 30. Let's say we just need to change the BOD. 30, 30, 31, 32, and then 28, 33. Right, so let's say this is our new BOD. And then let's do the test again. Okay, so now you see that a hypothesis is not rejected, okay, because the p-value is 0.4790. So basically here, the smaller the p-value, the more confidence we're going to have. So you can actually convert this p-value to a confidence level. So you can just use 1 minus p to, so here you can simply use 1 minus p to get the confidence level. So it's going to be 95% confidence that the sample is different from the population or the proposed population, right? But when it's at here, right, so we cannot really reject this null hypothesis, right? So, and this is the p-value we got. So in terms of the statistical analysis for any of these statistical analysis, we're going to talk a little bit more about other methods, but the smaller the p-value, basically the larger the confidence, or higher the confidence we are about our measurement. Okay, so this is the t-test function. As I said, you have to have the real data, real sample data to do the t-test. Okay. So then the next is basically we're telling right now what we're trying to do is that we're having the sample, we're comparing against the population, but there could also be scenario that we're comparing two different populations. So the scenario could be, let's say we have two rivers, right? So the two rivers and the factory is discharging pollutant to one river, and then the other river is just a branch of the previous river, right? So if we're having this bypass of the two rivers, okay? So, and the factory, we're saying that the factory is discharging water or wastewater at here, right? And then we're doing the sampling at these two branches. And the factory is saying that, well, we have a low enough BOD that after some time, the dissolved oxygen gets back to normal. And you can do a comparison between these two rivers and make sure and confirm that this is indeed the truth, right? So then we do some measurement of the dissolved oxygen concentration here and dissolved oxygen concentration here. And then it turns out that here the mean is indeed a little bit higher than the mean that we saw here, okay? So now we're comparing two different populations instead of trying to see whether one sample belonged to a certain population. We're comparing two different data sets, and we're doing the paired measurement. So paired measurement means that we're conducting measurement at the same time, or at least the same day, when we're taking the dissolved oxygen concentration, right? So let's say we took 30 samples, and then we find out the mean here is a little bit higher than the mean here. And then under this situation, how do we tell confidently that the sample is indeed different from each other, right? Or the samples are the same, or the two populations are the same. So we could again use the t-test. So now the t-test is going to be calculated in a different way. Instead of using this equation, basically we don't have the population mean anymore. We have to use a different calculation. Basically, we only consider the sample mean. So if we're taking two samples, then if we're taking two sets of samples, right, then it's going to the mean of the first set of sample, the mean of the second set of sample. In the denominator is 1 over the number of sample in the first group, number of sample in the second group. And consider the variation of the first sample group, second sample group, and then the degree of freedom. Right, so this is going to be the new t. And then how do we find the critical t? So then we're saying that this t is also going to follow a t-test. It's a t distribution. So the degree of freedom is going to be n1 plus n2 minus 2. Okay, that's different from the previous t-test also. Previous t-test is just n minus 1. Here, you have to consider the number of samples for both groups, n1 plus n2 minus 2. And then it involves the confidence level, right? So, or the significance level. And then the significance level, if it's one tail test or two tails test, then you're going to find the critical t based on this level we're looking for, right? So the table is going to be the same, but then you're going to have a different calculation for the t. So where do we use this? We said that it could be water samples, right, from the pollution, but a lot of times people also, or especially recently, people are starting to focus on the environmental justice issue. So there are reports saying that the poor neighborhood and the richer neighborhoods are exposed to different environmental conditions. For example, reports are showing that poor neighborhoods, they have a worse air quality, basically higher concentration of the pollutants, or the same applies to water quality, right? So basically, to confirm whether there is indeed a justice issue or not, we have to do statistical analysis. We're comparing two different data sets, right? So how do we prove that they're statistically different? So we're going to take samples at location A and location B, take their mean, and then calculate the t-values. So this is another example, right? So we can basically, let's see, this is example 1. And this is example 2. Okay, so the concentration of a particular toxic substance in the groundwater downstream of a landfill are shown to be drawn from a log norm distribution. So before the construction of landfill, we took 41 samples and standard deviation. We have the mean and standard deviation. But after the construction of the landfill, we took 21 samples, right? So the mean became higher, 0.623, and there's some standard deviation. So then the residents are complaining, well, hey, it could be that we built this landfill and then the toxic material leached into the groundwater, right? So can you confirm that these two data sets are statistically different, or are they statistically similar? So evaluate whether the post-landfill distribution of the concentration is significantly different from the pre-landfill distribution at 5% confidence level, right? 5% significance level. So we're talking about whether they're different, right? So we're not talking about one is higher than the other. So if they're different, then we're evaluating the difference, we need to evaluate the two-tail test, right? So whether could be much smaller or it could be much higher. So because of that, we have to use alpha being 0.025, right? So alpha being 0.025, and then the degree of freedom, 41 plus 21 minus 2, right? So that's 60. So we go back to this table, degree of freedom 60, and then 0.0252. So we're looking at the critical t-value of 2. So now we just need to calculate the t for these cases using this equation, right? So then we know that Tc equal 2. So if the t is between -2 and +2, then we say that they're not statistically different. If it's beyond this range, then they're statistically different. So now we can calculate t. T is going to be 0.563 minus 0.623, divide by this whole term to the power of 0.5, and 1 over 41 plus 1 over 21 multiplied by 20, say 40 multiplied by 0.021 equal 2 plus 20 divide by 60, right? So this is a whole expression, and then we can calculate. So the t-value turns out to be minus 0.4494, right? It's within -2 and +2. So basically, these two data sets are statistically similar at 95% confidence, right? So let me see. Well, should be 403, right? So the results are similar. So basically, the null hypothesis is accepted, right? So 5% significance level, 95% confidence level, saying that these two are not statistically different. Okay, so if you paid attention to the t-test, basically there are assumptions, right? So the assumption, the most significant assumption is that we're assuming the population satisfy the Gaussian distribution. Okay, but we also know that there are a lot of scenarios where the population doesn't satisfy the Gaussian distribution, right? So then, under this situation, how do we do the data comparison, right? So basically, there are other methods. There are a bunch of methods to do the statistical comparison of the data. So the next I'm going to talk about this is this Wilcoxon signed rank test. So they are being applied a lot of times on the non-normal distribution of the population data. So the Wilcoxon signed rank test, as you can see from the rank, this basically will involve ranking the data. Okay, so here I won't talk too much about the theory behind this method, but briefly we will go through the steps for using this Wilcoxon signed rank test. So it's being used for comparing two different populations. So it's similar to the paired t-test that we show in here, right? The only difference is that we don't need to make any assumption about this distribution of the population. So it could be, let's say, having extreme values in the higher concentration, which actually makes sense for the air quality, right? Because for air quality, if you think about the emission of the air pollutant, they're periodical, right? They're not always being emitted. Basically, during the rush hours, you're going to see high concentration of the pollutants, but most time of the day, the concentration could be quite low, right? So the air quality or the air pollutant distribution in terms of the population should not be following the Gaussian or normal distribution. Maybe it's following the log normal distribution, right? Or some other distributions. So under this situation, basically we're going to take the samples of the two different locations or two different populations. So first, we'll take this difference between the corresponding data points. For example, at location A and location B, at each hour, we're taking the air quality concentration. right? And then we take the difference between the data points. And then we note the magnitude and sign of each difference and rank the absolute values of the differences. So basically, you could be taking the difference. Let's say one location is always higher than the other one. Then you could be having the difference of 2, 3, 1, 4, 9, 10, and all of these different concentrations. But sometimes it could be minus, right? -5, -4. And then we take the absolute, basically take the absolute value of all of these rank differences, all of these differences, and rank them from the smallest to the largest. Okay, with the smallest difference giving the rank of 1, the largest difference giving the highest rank. So in case there are magnitude ties, for example, some location, the air pollutant concentration difference could be always like 2 milligram per cubic meter, right? So then each difference is given the same rank. So basically, not only they are given the same rank, but we should be using the average rank for these same ranks. So for example, if they're having the difference of 2, and then their rank being 1, 2, 3, and then we give the same rank, but the average ranks. So it's going to be 1 plus 2 plus 3 divided by 3. Okay, so giving them the same rank of 2. And third, the ranks are attributed to the positive and negative differences, and are separately summed, right, and denoted by S plus and S minus. So basically what that means is that we further separate these ranks based on whether they are positive differences or negative differences, and then we separately sum all of these positive ranks and the negative ranks. Right? So this is why it's called the signed rank test. So we're basically having the rank and then consider the different signs. So then we test the S. Basically, it's the minimal value of these two different summations of the ranks, right? So for example, it could be having a minimum value of the summation rank being 40, right? And then basically you are calculating this z value, right? The z value being s minus mu s divided by sigma s. The mu s is being calculated by n multiplied by n plus 1 divided by 4, where actually n is the number of samples we took, right? Sigma s is the variation, right? So basically, this is the mean and standard deviation, mean and the variation of a normal distribution. So I wouldn't talk about why this is the case, but this is basically how we do the calculation. These are the steps. So then again, you use the n to calculate this the variance. And based on the normal distribution, then we can tell whether again, with a Gaussian or normal distribution, we can integrate the at different critical z values and compare the z value that we calculated and the critical z value, and to see whether the two populations are indeed different or they're similar. Okay, so this is a z distribution. Basically, it's a normal distribution, right? You can see that z start from negative side, and then we could be taking, let's say, 0.92, 0.93, and then this is a probability, right? So it's similar to what the t distribution is about. So here, this is an example. So basically, we're taking the measurement at the entrance and exit of a treatment process. It could be BOD treatment, right? The corresponding paired measurements are as follows, right? So this is at the entrance, this is at the exit, right? So you can see a lot of times you see, sometimes you see lower value of the at the exit, right? Sometimes you see higher value at the exit. So then how confident are we to say that these two measurements or the treatment process is effective or not effective, right? So determine whether there's a significant difference between the means and entrance, means of the entrance and exit data set. Okay, so this is our example 3. So we can first put our entrance here, entrance 40, 50, 40, 46, 50, 9, 9. Okay, so this is our entrance. We have our exit. So these are our data sets. So if we follow the steps, right? So the first step is to take the difference, right? So the difference is going to be exit minus entrance, right? So also let's make this data set to be vertical so it's easier to show the values. Okay, so this is our difference. And then, as the method says, we need to take the we need to first note the magnitude and sign of each difference, right? And then we rank the absolute values of the differences. So we need to calculate the absolute values, right? It's going to be ABS differences, right? So let's just make this term to this difference to be the first column, 1, and the second column would be Q, right? And then, so if we show that this is our absolute difference, right? So then we need to rank all of these parameters, all of these differences based on the the magnitude from the smallest to the largest. So for example, here, this is taking the value of 1, right? So then we should be taking, putting 1 here. I mean, 1 for the first one, 1 for the second one, and 1 for the third one. So, well, you could do that in the writing way. So for example, just write out like say 1, 1, and 1, we give the rank of 1, 2, and 3, right? And then maybe it's easier to do it on pencil and paper, right? 2 be giving the number of 4, the rank of 4, and then so on and so forth, right? So basically this is what you're going to see. And then the other thing that we mentioned is that in case of the magnitude ties, we're going to give it the same rank. And actually the same rank is going to be the average rank. So for example, we know that in terms of differences, there are like 3 ones, right? So theoretically, we'll give them rank of 1, 2, and 3. But actually, the average rank is going to be 3, right? So 1 plus 2 plus 3 divided by 3. The average rank is which is going to be 2. So because of that, we can rank these absolute values for the negative differences and positive differences, right? For example, negative difference is going to be 2, 2, 2, 4, 8, 8, 15, 14, right? Because negative 8 has a rank of 14. So the sum of all of the rank is 40, right? So at the same time, we can calculate the mean value and the standard deviation using the basically 15 as the n here. And then you're going to have 60 and sigma s 17.6. You can calculate the z, which is minus 1.15. For a 5% significance level, you can find out the critical z value, which is 1.645. So if you go to this table here, right, so we're looking at 5% of the significance level. So you can see basically it's between these two values, right? So it's going to be 1.645, right? So it turns out that, well, our calculated z value is larger than the critical z value, right? So which means that null hypothesis is accepted, right? So it cannot be rejected. So basically it means that these two data sets, they're not significantly different from each other, okay? So in terms of the MATLAB function for the rank sum test, so again, you can see that the Wilcoxon, the rank sum test, basically it doesn't have any requirements for the distribution of the data. So that's why it's going to be more convenient when we don't know how the population looks like, right? So you don't have to use a t-test, which assumes the log normal distribution, or assume the log normal distribution. So in terms of the MATLAB function, you can use the rank sum function. So you can just do help rank sum. So basically, you can, again, calculate what is the p-value and what is whether the hypothesis is rejected or accepted. and then you can provide two different data sets. So if you want to do that, let's first comment all of these lines, right? So you can just do PH being rank sum of entrance and exit. Right, so you can see p-value is very large, right? It's relatively large. So that's why the null hypothesis is not rejected, right? It's accepted. So which means that these two data sets are not statistically different from each other. Okay, so this is the Wilcoxon test, right? In this class we learned about the t-test in more details, and Wilcoxon test we run through the process, and then nowadays you also hear a lot of people talking about the ANOVA test. Basically, ANOVA test is short for analysis of variance, right? So take the ANO and VA. It's ANOVA test. So people use the ANOVA test basically to determine whether there are statistical difference between three or more independent groups. Okay, so when you have multiple groups, then we use ANOVA test. So you can imagine now we have three different samples, right? Let's say three different branches of a river, or let's say three different locations of a river. So if you want to test whether they're statistically different, you could use a t-test to test like A and B, whether they're different, B and C, whether they're different, C and A, whether they're different. But now it's getting more complicated, right? If you have 4 groups or 5 groups, then you have to do so many t-tests that it's going to be quite labor intensive. So then what we can do is we can do this variance analysis of variance test, the ANOVA test, which considers more independent groups, right? So it works by comparing the variability between groups to the variability in each group. So basically it's assuming that if they're indeed from the same group, then the population's variance is going to be similar to the variance in each group. So it's using the F value, which is a ratio of 2 variances. So then basically it's the variance of, one is a variance of the entire group and the other is variance of within each group, right? It's considered each group. So basically it calculates this mean square error. Okay, so it's calculating this mean value and then considering basically the error or the deviation from the mean regarding each group and regarding the population, right? So it works for the case of multiple sample groups, and null hypothesis, there's no difference. Again, you can calculate an F, find the critical F value, and then tell whether the data is different or similar to each other. And especially, you can think that if we do certain experiments, and then we do different batches, for example, we could be doing a set of experiment today, a set of experiment tomorrow, right? If they're independent groups, we want to make sure that there are no differences in terms of the time, or there are no differences between students. You could have 20 students doing the same experiment, right? But because of the procedure, the protocol, different people understand the protocol differently. Maybe the result is going to be statistically different from each other. So under that situation, we could use this ANOVA test to see if they indeed agree with each other, right? Whether they're statistically different from each other. So again, you can see that we could calculate the F, and then there's this table for F value, right? So you can see a lot of these sample statistical analysis, we have to use a table, right, to find out the critical value for the criteria, either the T value, the Z value, or the F value, right? And then we can tell whether the null hypothesis is accepted or rejected, okay? So that's it for this class. And here in this class, basically we analyze or introduce different methods to tell whether the sample belong to a population or agree with the population, or whether the sample of different populations agree with each other. And basically there are also methods in MATLAB, or you can also use other online or computation tools to calculate these statistical values. So basically in the future, when you see the description of the confidence level or the p-value or the alpha value, you don't need to be scared, right? Basically, it's just doing some simple calculation and referring to a specific table. So that's it for this class, and let me know if you have any questions.